Hi everybody, and welcome to the first VTSS of the new year. We're gonna start the year with Katerina. Thanks a lot for joining us, and let me thank also Ioannis for joining us as a panelist. Katerina recently moved to Kasparis in Venice, so she's in her new office. She's gonna walk us through her project, and the rules of the game are the usual. So we've got around an hour for the presentation. Feel free to unmute and ask questions, usually clarification questions. If you have more substantial points, maybe we can just wait until the end of the talk, or we turn the recording off, and then we start with the discussion. Katerina, off we go, and thanks a lot for accepting the invitation.
Thank you so much for inviting me and for letting me be the first speaker of the year. So this is a joint work with Tassos Magdalenos. It's a gigantic project that has taken us a very long time to revise and to rewrite. So some of you have actually seen versions of this paper. It's now second round revising and resubmitting the review of economic studies. And in the first round, we've already submitted the first revision that was accepted. Like now we are doing the second one, but I'm going to present you the plain vanilla paper, like the one that without all the bells and the whistles that we were asked to add in the revision, because for me it's important to present the main idea. And I will, in passing, I will mention the additions and the extensions that we have done in order to satisfy the referees. Okay, so let me start directly with the motivation for this paper. Consider being in a predictive regression setup. So here, YT, everything is scalar. Everything is going to remain scalar for the duration of this talk. I will talk about possible multivariate extensions at the end of the talk. So YT is some time series that depends linearly on some ft minus 1 measurable regressor xt with some slope coefficient beta. And the xt regressor is generated as a first order stochastic difference equation, where I will be more specific about the assumptions that we make. We will add an intercept and so on. Also, we'll be more formal about the assumptions and the innovations. But the key thing here is that we're allowing this root to be sample size dependent, and I'll talk about why we need that, and that's one, in a way, that would be a device for us to derive properties of the test statistics. But let's talk a little bit about what's the problem in this model. Whether you're in equation 1, you're trying to make inference on beta, so you're trying to construct confidence intervals or test a hypothesis on beta, and rho is just a nuisance. You never have to estimate equation 2. Or whether you're in equation 2 and you don't even have a predictive regression. In both of these cases, and actually in the paper we also add a local projection model, and that's a third model where exactly the same problem happens. So what's the problem? The problem is that both the rates of convergence and the asymptotic distributions for rho, for the Euler's estimator for rho, the Euler's estimator for beta, and the Euler's estimator for the local projection parameter, all these asymptotic distributions are vastly different depending on the persistence regimes of X. That is, depending on the regions in which this sequence rho n converges, let's say. And as such, if you don't know ex ante what type of animal your regressor is, whether it is a local tuner root or explosive or stationary or oscillating and so on, then you are running the risk to construct invalid confidence sets for these parameters in applied work. And in terms of empirical relevance, the first example that comes to mind is if you think about, for example, inflation series, which are heavily used and abused in macro. And this type of data are characterized by a very large degree of memory of persistence over time. And whether you have structural or reduced form models, every time you include inflation on the right-hand side of these models, both reduced form and structural, there is the risk that maybe confidence sets, and that is confidence intervals for hypothesis tests on the parameters of this regressor inflation, it could be completely invalid, and that's an asymptotic problem I'm going to talk about. Other relevant application, like the biggest one that you have on predictive regression, that's equation 1, is the sort of is really predictability in financial asset returns. So what people do is they run this regression, equation 1, where they have on the left-hand side asset price returns, which are very much like, noisy, right, and not persistent. But on the right-hand side, they include predictors, right? They're trying to forecast returns. That's a big deal, right? If you can forecast returns, then you can make money, potentially, whatever. So on the right-hand side, they include stuff like dividend price ratios or earning price ratios, very, very persistent regressors. And what they find is really highly significant beta. But this literature from the 90s that some of these papers have now been shown to be completely wrong, because when they were finding predictability, what they were really finding is that the regressor is very, very persistent. So that predictability was spurious. There was no real predictability. It's just that the regressor was too persistent, and therefore they were getting these huge size distortions. So rejecting the null one, they shouldn't be rejecting. This type of, I would talk about bubble testing as well. So, you can get, equation 2 has been used for testing for bubbles, where explosivity, under explosivity regime, you have basically a bubble inflating in some sort of an asset price, and under the null hypothesis, you have efficient market hypothesis. So, so it's like one-sided unit root type test. But, this type of, persistent data can also show up beyond economics, in epidemiological models, climate, and so on. So there is, there are potentially a lot of empirical examples. The main thing is every time we include a right-hand side variable that's very persistent, we should be worried about the fact that maybe, the inference may be completely invalid if we're not making the right assumptions. So what we do in this paper, we try to provide an inference procedure, which will be for general autoregression. So it will be equation, like we will be dealing with all three models with the same procedure, both all the predictive regression, the autoregression, and the local projection, which I'm not showing you, but it's in the paper. All these three models will solve it the same way. We're going to aim to provide an inference procedure that's going to be valid for these parameters, and will have uniform size. Okay, so our size would not depend on nuisance parameters, and I will be more specific about which nuisance really we would include in the parameter space. For any root that sequence rather in n row n that converges anywhere in minus infinity infinity. So we could this allows for stationary, near stationary, local to unit root, pure unit root, mildly explosive, purely explosive, oscillating, seasonal unit roots, all of that. And we'll cover this with one procedure. So the contribution of the paper is kind of twofold. First, we're going to be constructing an instrumental variable that will be constructed from the data that will cover sort of explosive regions. And then we're going to use a data-driven approach to combine this new instrument with the existing IVX procedure of Phillips Magdalenos that only works between -1 and 1. And we will have the new combined procedure, which will be automatic and data-driven. So there is no choice to be made. It automatically selects the instrument, and you'll see exactly how it works. We'll have no discontinuity in the limit distribution. So we're going to have mixed Gaussian limits in all cases. And we're going to, because the mixed Gaussian limits will be different in different regimes, but crucially, the t-statistic, which is self-normalized, so magically, the t-statistic will cancel the possibly random denominator in the mixed Gaussian limits, and therefore, our t-statistic will be standard normal in absolutely all autoregression regimes. And we will show that our t-statistic would also have uniform size. So our size, the size of our test will not depend on raw, and it would also not depend on this on the distribution function of the innovation. So we will show uniformity over this infinite dimensional object, which is the CDF of the innovations. I'm going to talk a little bit about the explosive case, because as far as we know, in the purely explosive case, this is the first procedure that's semi-parametric, that doesn't require knowledge of the distribution of the innovations. I'll talk a little bit about that. And for presentational purposes, and also because I'm a little bit dyslexic, I'm going to focus on -1 to infinity. And then I will have one slide to show you how we can incorporate -infinity to infinity. It's basically a mirror image. It's just because absolute values and left and right, and you should see how I drive. So the plan for my talk is a little bit to discuss the motivation and different persistence regions. I was trying to judge a little bit from the list of people who are attending, just to understand you know, whether everybody's time series or not. It's because I present this paper in different places, and you know, usually for a more general audience, I spend more time talking about the problem, because I don't want to assume that people remember the problem. But I think that given this is a more econometric audience, I can go faster through the motivation and spend more time on the methodology. But I will still talk a little bit about the problem before I talk about the solution. I'm going to talk about the main assumptions and the main results. This is the plain vanilla one, but I will also mention the extensions that we've done. Then we have a very large amount of Monte Carlo simulations, where we compare to, in all the 3 different models. We compare with Andrews and Guggenberger in the autoregression. We compare with Elliott, Muller, and Watson procedure in the predictive regression. We compare to Klogborg, Muller, and Olea in the local projection model. So I will have all the simulations. And then for the applications, we have 2 applications. We have one for epidemiology, which is a little bit, it's a little bit boring. Maybe I skip that. But the new application is on testing for bubbles in the Magnificent 7 text docs. Okay. So maybe I mentioned that a little bit. Okay, so in terms of motivation, just to remind you what the problem we're trying to solve before we talk about solution. What is the problem? Well, if rho is strictly between -1 and 1, or if actually rho n is a sequence that converges anywhere strictly between -1 and 1, there is no problem. Basically, OLS works, not only works, it's square root n consistent, asymptotically normal, that is statistically standard normal. Everything works as if you had independent data, even though you have memory, which is because you have very short memory. So over here, there is no problem. Now, when rho is equal to 1, or in fact, when rho is, in our case, rho n is a sequence converging to 1, either from above or from below, at rate n or faster than that. So this is an area that has been branded in the literature as a local to unit root. In that world, basically, we have different limit theory, right? So we have functional central limit theorem to Brownian motions of the use of the innovations in the autoregression, the epsilons, the innovations in the predictive regression. So partial sums of the u's in the epsilon converging to this weakly to these Brownian motions, and the partial sum of the x, the autoregressive, the autoregressive process converging to Orson-Uklebeck process with coefficient c, where here you have this integral that depends on b. And OLS estimators are still consistent. In fact, they are super consistent. So they converge faster to the truth. They converge with ret n rather than square root of n. So if you care about point estimation, you cannot outperform OLS here. But if you care about constructing confidence critical regions, confidence intervals, or hypothesis tests, then this animal here, like Phillips and Chan and Wei show, the limit distribution is this ratio that involves stochastic integrals that are a function of this, Orson-Uklebeck process. And so, in general, doing inference here is very hard, because if you know that you're in exact unit root, so c is equal to 0, you can simulate critical values from here. But if you don't know that, if you are in the general local unit root region and c is not 0, these critical values depend on c, and so you cannot simulate directly And in fact, you cannot estimate C because your less estimator for C is inconsistent. So that's a kind of a big problem in this local unity region literature, and this has generated a vast literature in finance, including Campbell Nyogo, Jensen Moreira, Econometrica, Elliott Muller, and Watson. Just trying to solve this one small region problem. Now, what about the purely explosive case? That's more exotic, but we really like it. And for us, it was like, actually, this is how we started this paper. So if rho is strictly greater than 1, or if it's converging somewhere above 1, this is an old literature that goes to the sort of late 50s by White and T.W. Anderson in the Annals of Mathematical Statistics, where T.W. Anderson shows that if the innovations in the autoregression are IID, and the initial condition is 0. So without IID, and things get very messy, and initial condition actually features in the limit distribution. So that's why this is already strict, is restrictive. But under these two additional conditions, the OLS estimator for rho is hyper consistent. So it has exponential rate of convergence. So converges really, really, really fast, that's true. However, the asymptotic distribution is of unknown form. And in particular, the asymptotic distribution is a ratio of two random variables, which are asymptotically independent, whose limiting whose distributions we don't know actually. For example, if you take z infinity, the denominator is the almost sure limit of some weighted sum of innovations, where because rho is greater than 1, these things are decay exponentially fast. So this animal z infinity converges. Rather the sum. This sum here I cannot mark. Converges by the martingale convergence theorem, and it converges crucially without any normalization. So one way to think about why there is no central limit theorem, both in the numerator and in the denominator, is that this sum converges without the need for normalization. The thing is that when you normalize, like if you, in the standard case, when you divide by 1 over square root of n, each term in the sum becomes negligible. And this is the kind of asymptotic negligibility condition that you need for the central limit theorem. But here, there are terms inside that sum. For z infinity, it's the first few terms of the innovations. For y infinity is the last few terms of the innovations that drive the entire distribution. That basically, if you change those finitely many terms, you will change the limit. And that actually violates a necessary condition for the central limit theorem. And that's why there is no central limit theorem here. In fact, and it happens that these guys converge by the martingale convergence theorem. But so this is the intuition. And if you compute the t-statistic based on the OLS estimator in this case, it is completely driven by the limit distribution of y infinity. But y infinity is driven by the last few observations of the innovation. So the last few observations of the innovations in the sample carry the entire distribution of the t-statistic. So we don't know what the limit of the t-statistic, what the limiting distribution of the t-statistic is in the purely explosive case, in general. Now, White, in his paper, says, what if the U's are IID and Gaussian? If the U's are IID and Gaussian, then this sum is a sum of Gaussian animals. And so it's Gaussian. And in that world, under Gaussianity, White derives using some moment generating function approach. White derives the limit distribution for y infinity and for z infinity. Both of these are normal, independent from each other, with the same variance. So at the end, you get the ratio of two standard normal random variables. So that's the Cauchy result that White derives. But that only happens when the initial condition is 0, the user IID, and the user Gaussian. In general, we don't know what the limit distribution of the t-statistic is. So there is no, as far as we know, there is no semi-parametric procedure that can give you confidence intervals without specifying distribution for the innovations. What about beta in the predictive regression? In this type of models, both the local projection, the predictive regression, and the autoregression, everything is driven by rho. So the limit distribution for beta is exactly the same, like the limit distribution of rho, meaning it has the same rate of convergence, which depends on rho. It's exponential rate. It has this scaling, this constant scaling, which depends on the standard deviation of the u's and standard deviation of the epsilons, and it has the same form. It basically has weighted, y infinity is now weighted epsilon sum, and z infinity is the weighted u that you saw from the previous slide. And again, the result is exactly the same. Unless the epsilons and the u's are IID and Gaussian, you cannot derive limiting distribution. You don't know the form of the limiting distribution for the OLS estimator. In the special case of Gaussianity, you get Cauchy distribution, and the t-statistic and the Cauchy distribution being mixed Gaussian means that the t-statistic self-normalizes, and in that case, you have standard normal t-statistic, but in general, you don't know the form. And this is just a quick simulation to demonstrate exactly the problem. Consider having, I have a huge amount of simulations later on. This is just to show you this, to show you this particular intuition about the explosive case. Rho is 1.09. I have IID Gaussian innovations. Everything is perfect. I have, I'm going to show you the empirical size of the 95% two-sided t-test for beta based on 10,000 replications. So under the null. So that needs to be 5%. Okay, how much you reject the null under the null. And here, the only thing I'm doing is I'm changing the last observation for the epsilons. So I'm changing one innovation out of n, right? So if you had any central limit theorem, even if this thing caused some distortion, that should wash away as I increase the sample size. That's what the central limit theorem will tell you. So if epsilon 1 star, the last observation is drawn also from a standard normal, there is no problem. So you can see that, with really, really fast, you get the 5% size. Perfect. If epsilon 2 is, epsilon star is 2, but this is just one observation that has a slightly different variance, but it's the last observation that carries big chunk of the distribution of the t-statistic. You can see that you get big distortion. The problem isn't the distortion. The problem is that as I increase the sample size, the distortion not only doesn't go away, it actually gets worse. And if I can make this 100%. If I can distort this completely. Like I'm just showing you an illustration. So that one observation changes everything and ruins the size here. Okay. So now I've talked to you about stationary unit root and explosive. I'm gonna talk a little bit about two intermediate periods, regions, not because I'm pedantic. I mean because I'm pedantic, but also because these two regions are going to be important for our procedure. So these are the our instrument that we're going to build is going to be artificially made to belong to one of these two regions. Okay, so that's why they're important. So the nearest, what I'm gonna call near stationary region is it is a region where rho n, the root, is converging to 1 from below, but it's converging at a rate slower than n. So this is outside the local unit root region. And I think that this was part of Tassos' PhD thesis. So I think the motivation for, they wrote a paper with Phillips in 2007. What the motivation for that paper was, what are all these jumps? Like here you have square root of n, here you have n, here you have rho to the power of n. So, there is these discontinuities in the rates, these jumps, and clearly they cannot be jumps. So there's stuff in between. So they were trying to fill the gaps in there. And what they found out is that if the autoregression belongs to that region, then sample moments, like sample variance of x, normalize with a slightly faster rate than n, so 1 over n times kn. So here this goes, kn goes from 0 all the way to n. So you can go all the way to n squared, almost to n squared to the local unit root, right? So you have fast rate here, but crucially, the sample variance converges to a constant, not a random variable anymore, like in the local unit root case. So you don't have random random limit here. You have a constant. So what they were saying is, well, this near stationary region, the boundary between that and local root is the boundary between ergodicity and non-ergodicity. Here, processes have sample variance converging to a constant. Here, they have sample variance converging to some nasty random stuff. Okay, but not only that, if I was to consider xt minus 1 ut, which will be what will be in the numerator of my OLS, right? But it would also be in our numerator for the IV estimators that are going to come. That thing satisfies the martingale central limit theorem, and it converges to a normal distribution. So that's very nice. And so if they were to, so here I'm describing you this region as if the true data generating process X belongs to this region. Now you may say, Katerina, this is completely irrelevant empirically, and I will tell you that's fine. But we want to know the properties of this region because our instrument is going to be constructed artificially to belong to this region, and it's going to satisfy a martingale central limit theorem. That's the game, even if never we encounter data that behaves this way. So, but for the moment, let's pretend that X is generated in this way. In that world, if I compute the OLS estimator for rho or for beta, if my X was a true linear stationary process, I get asymptotic norm. I get asymptotically normal. Distributions, estimators, and faster rate of convergence. So this kind of bridges the gap between root n and n, because the rate here can go from root n all the way up to but excluding n. Okay, so that's the first thing that they do. Now in that same paper, they also consider the exact mirror image of the near stationary process, which I'm going to call mildly explosive process. And here rho n, the sequence rho n converges to 1, but it converges from above, and again converges at rates slower than n. And in the same paper, and this is the thing that is slightly more counterintuitive, what they show is that if I consider the OLS estimator for rho, given that my X was a mildly explosive process, I'm going to have something that looks very similar to the purely explosive case. Particularly, I'm going to have the exponential rate slightly slower than the exponential rate here. And I'm going to have a ratio between two sequences, Zn and Yn, exactly the same sequences, like in the pure, exactly the same algebra, like in the purely explosive case. But the only difference is that now Zn, remember my Z infinity was the almost sure limit of this sum here. I don't know if you can see my mouse, of the weighted sum of the innovations. Well, now that thing blows up because rho n now is no longer greater than 1 or converging from the greater than 1. So these guys blow up, this sum. And because it blows up, it needs a normalization. The normalization happens to be 1 over square root of Kn. And it turns out that exactly the same normalization for the numerator. And now once you divide by 1 over square root of Kn, with Kn's blowing up, you have asymptotic negligibility. You have uniform asymptotic negligibility because no term, if I now consider a term inside this sum, no term can change the limit because all of them are divided by something that goes to 0. We're divided by something that goes to infinity or multiplied by something that goes to 0. So this is the game. And so it turns out, this is not the only reason, that is a necessary condition, plus together with the Lindenberg condition, to show that the martingale central limit theorem operates both on Yn and on Zn. Then you can, what they show is these guys converge in distribution to two normal distributions, which are independent. So these two are asymptotically independent. And therefore, the OLS estimator for rho and for beta are both Cauchy. And their Cauchy ratio of two independent standard normals, regardless of the distribution of the innovations. Remember, that was not the case in the purely explosive case. That was, only on the Gaussianity. Here, this happens for any So here you don't have martingale convergence theorem. Here you have martingale central limit theorem. And so this is very nice. And again, you may tell me, Katerina, who cares about model explosive processes? This may never be encountered in real life. And the point is, we're going to construct our instrument artificially to have the persistence properties of a model explosive process. And by doing so, we're going to inherit the martingale CLT that's going to allow us to do the test statistics to get the limit distributions, okay? So up to here, I'm just talking about the problem. Now, let me just in one slide tell you about Phillips and Magdalena's IVX, because that's a building block in our procedure. So they have a paper where they cover, inference from stationarity, including near stationarity and local-tuner root. So all the way up to local-tuner root. So what do? They're in that framework that you saw before, either predictive regression or autoregression. You don't know what the true regime for X is. They construct an instrument process Z. So Z is a artificially created sequence that we built. They do that by accumulating some innovations, quasi-innovations. In their case, these quasi-innovations are delta X. So you take first difference of the X's, and you accumulate them in an autoregression of order 1, where you pick the root rho and z. Rho and z is chosen by you, and it's chosen to belong to the near stationary region, okay? And so what they do is now they say, we're going to use z as an instrument. So it will be like as if you project, X on Z, and then you use the projection instead of the original X in the regression. That's one way to think about this. And so they consider IV estimator, literally Z prime X inverse Z prime Y for rho, and the same for beta. And the game in their estimation is the following. So, their estimator is the true rho plus, plus this ratio. So if you look at this ratio, so the numerator is the important one, is to get central limit theorem for the numerator. So what they show is this: there's two cases in their world. If you pick an instrument that belongs here, its persistence here, somewhere here. If the true process it was more persistent than the instrument that you chose, okay, then they show that this ZT process behaves like a true near stationary process, okay, as if these things were the true unobserved U's, okay, and in that world, ZT minus 1 times UT behaves like, satisfies a martingale central limit theorem, like I showed you in one of the previous slides. That's if your true process were more persistent. If the true process is less persistent than the instrument that you chose, then what they show is that ZT behaves like XT plus some OP terms you can control. So then you are instrumenting with the process itself, so you get OLS. But OLS is valid anywhere here, all the way up to here, right? So then, you just get all the optimality that OLS brings, okay? So that's what they do. The same stuff happens from beta. And, what they show is that their IV estimators basically have mixed Gaussian distribution. By the way, the denominator here could be very nasty, because if the true process is unit root or local unity, the key first thing, this instrument is relevant. So it's because it's constructed from the data, it's never going to be zero. Like it's going to be relevant. So you're not going to have problems where the denominator goes to zero, because it's chosen to be relevant. But establishing the limit of the denominator, especially when X is a local unit root process, this thing will be random, possibly random limits involving stochastic integrals and so on. So they have mixed Gaussian distribution, in which in some cases they have a random variance. However, they can show that asymptotically the denominator is independent from the numerator. And therefore this random variance basically cancels when you consider self-normalized tests like that t-statistic. And that's why they get standard normal t-statistic in all these three cases, okay? So the first thing that we do is we actually want to do inference on the right side of unity, where, you know, as far as we know, it's an uncharted water. Like we don't know of a semi-parametric procedure that works in the pure explosive case. And so we're going to be constructing an instrument in a similar fashion, but with two important differences from Phillips and Magdalenos. Number one, our route will be chosen to be mildly explosive. Okay, so it's going to be converging to one from above. So our instrument is going to behave as a mildly explosive process, not as a near station process. And the second is we are not going to take first difference. Our quasi-residuals, the stuff we're going to accumulate, are not going to be the first difference of the x's, because if x is a purely explosive process, you can difference it infinitely many times. It's not going to help you. Instead, we're going to do first stage OLS. Fit the residuals, because OLS, remember, is super consistent in this case, hyper consistent. And then we're going to use the OLS residuals to accumulate those. So these are the two important differences. Our instrument will always behave like a mildly explosive process, regardless of whether it's more or less persistent than the true process. And and we're going to basically have a martingale CLT for our numerators, because our numerator will be something like this, ZT minus 1 UT, and ZT would always be a mildly explosive process. So we'll have a martingale CLT, just like in the mildly explosive processes of Phillips and Magdalenos 2007. Okay, so I mean, one thing I want to stay on time, so I need to go faster. But one thing I want to say, like here, you might say, "Well, Katerina, this is super arbitrary. Like, why are you accumulating with AR1? And like, why are you picking the root? Like, you know, why are you accumulating there?" So, just to give you a bit of flavor, what we're working is we know various extensions, including multivariate extensions and also extensions with richer dynamics. The reason why the instrument here is an AR1 is because the true process is an AR1. So it turns out that when we are working in the ARP case or the VRP case, where we have P lags, our instrument also needs to have, needs to be an ARP process, and then we have ways to pick things. So this is not arbitrary. This comes from the data generating process of X. Okay, so the main contribution is to combine Phillips and Magdalenos with the new mildly explosive instrument, because what we would like to do is cover the entire parameter space, and we would like to have a data-driven procedure so that when people use this procedure, they don't have to do pre-testing, and they don't have to, take make any arbitrary choices. Basically, the procedure works automatically. Okay, and so we're going to do this in the following way. So the crucial thing is that both instruments work in the locus unit root case. So they overlap here. And so what we really need to know is we need to know the sign of C. If we parameterize rho, the true rho to be 1 plus C over Kn, what we really need to know is the sign for C when we're outside the locus unit root region. And we're going to use this quantity, n rho hat minus 1. This is going to blow up either to minus infinity whenever the true x is stationary, near stationary, or to plus infinity whenever the true x is mildly explosive or purely explosive. In the locus unit root region, this thing is just converges in distribution to some random variable. So in the locus unit root case, we won't know if C is positive or negative. We won't know if we're in the right or the left. But outside the locus unit root region, we can determine that. And so we're going to construct our combined instrument Z to be, again, a first order autoregression, because our model is first order autoregression, with root chosen, rho and Z, which will be a near stationary root whenever this quantity is smaller than 0, n rho hat minus 1, or a mildly explosive root whenever this quantity is greater than 0. And we're going to have innovations. We're going to, accumulate the quasi-innovations, which will be either the delta x's whenever you are stationary, near stationary, and the U hat OLS whenever you are mildly explosive. That's the idea. In the locus unit root case, what's going to happen is both the mildly explosive and the near stationary instrument will contribute. And they will, well, you will see that when I show you the limiting distributions. So we're going to have an instrument that behaves as a near stationary process here in the stationary and near stationary region, behaves as a mildly explosive process here in the mildly explosive, purely explosive region, and it's going to behave like a linear combination between mildly explosive and near stationary instrument whenever the true process is local tuner root. But crucially, both instruments work in that case, and this linear combination will still allow us to preserve mixed Gaussianity in the local tuner root region. That's the game. Okay, so let me give you the sort of the plain results under the very vanilla assumptions. So that's the very early version of this paper. As I said, now we're like revising second time. So things have changed, but mainly we have been asked to add a lot of extensions, and I will mention those in passing. So everything's univariate in this paper. As I said, we're working on the multivariate extensions, but not in this paper because the paper is already gigantic. In the paper, we have an intercept in X. It doesn't change anything, so we can have an intercept in X. Here, V, our innovations epsilon ut, we're going to make the following assumptions. First of all, for the parameter space, like I said, I'm still in -1 infinity. I will tell you one slide how we do minus infinity infinity. It's just a transformation. So we're considering a real sequence rho n that converges to any arbitrary point in minus infinity in the paper in minus infinity to plus infinity. You can think of this if you don't like if you don't like sample size dependent parameters, because I don't as well. I think as a DGP makes no sense. You can think of this as a device, because what we're going to show is that for an arbitrary sequence rho n that converges anywhere in the parameter space, our T statistic is standard normal. And because of that, we can claim that the size of our test is uniform over rho. Okay, so it does not depend on any nuisance parameter involving rho like C, like the latency. Okay, so this is, this is just a device to show uniform. If you're Tassos, you believe this is a data generative process. If you're me, you believe this is just a device to get nice properties for the inference procedure. For this version, I'm showing you conditional homoscedasticity. So I'm assuming that the epsilons and the u's are martingale difference, conditionally homoscedastic, and square uniformly integrable. However, in the paper, we have added heteroscedasticity. So we have, stationary gauge type heteroscedasticity. And then, of course, we have our test statistic needs to have a heteroscedasticity consistent standard error. Okay, so that's possible, and that's in the paper now. And we have some condition on the initial condition. So the initial condition is very general. In the purely explosive and the purely stationary case, it can be big OP1, so bounded improbability. In the case when rho is converging to 1, it can actually diverge. So the initial condition can diverge, but not too fast. And this just gives a constraint on how fast it can converge. Now, the way we did the proofs, which may not be the most economic way, is to show the limit distribution, the mixed Gaussianity for our estimators under a slightly stronger assumption 1 star, which divides our process into near stationary, local tuner root, and mildly explosive. And then the most important thing, our T statistic is proven under the more general assumption 1. And we need that because this plus some other conditions give us the uniformity. Okay, so I will mention somewhere how we go from assumption 1 star to assumption 1. But assumption 1 star is slightly stronger than assumption 1. That's okay. I already told you how we construct the combined instrument. I've changed a little bit notation here. I realized that I started changing the slides, but if you start messing with the notation in the last minute, if you don't change it anywhere, it's a mess. So I thought it's better to leave it. So here, rho n z is still the chosen root for the instrument. Phi 1 is the near stationary root. phi2 is the mildly explosive route. These are both chosen by the researcher. And I will mention in the Monte Carlo how to choose the choose the kappa sequences. So we have some rule of thumb, and we have a lot of results on that. Theoretically, any kappa 1 and kappa 2 that converge to infinity slower than n will work, but in practice you have to choose them, and I will talk a little bit about that. The instrument process I showed you before, right? So it is near stationary. So the instrument behaves as a near stationary process whenever the true x is stationary, near stationary, behaves as a mildly explosive process whenever the true x is mildly explosive or purely explosive, and in the local route, it behaves as a linear combination between this Z1 and Z2, okay? And then these are the building blocks. So this in the paper, this is one huge theorem, but I've broken it down into 3 pieces. These are the building blocks. Remember, the main result is a lot more clean and like elegant. But before that, let me mention the results that we need to get to the main result. And this is basically under assumption 1 star. We have these 3 regions for x. Near stationary, stationary, local to unit root, mildly explosive. We're going to get the limit distribution in all these 3 cases. So here we're considering rho tilde n is the instrumental variable estimator based on this new combined instrument that I showed you in the previous slide. Whenever the true x is stationary or purely or near stationary, then the limit distribution of our IV estimator is basically normal, not mixed normal, just normal. In here you have embedded the variance and also the rate of convergence. So what is the rate of convergence? Well, basically it is square root of n times square root of the minimum between kn and kappa 1, and kappa 1 is chosen. So this is really just plain vanilla Phillips and Magdalenos IVX. This part is not new. In fact, because our combined instrument basically chooses the near stationary instrument of Phillips and Magdalenos with probability 1. So, it's the same thing. If you instrument with something more persistent than the true process, then you get OLS rate, efficiency, equivalence with OLS efficiency, etc. If you instrument with something less persistent than the true x, but true x is still near stationary, then you lose a little bit of rate. Instead of having square root of n times square root of kn, you get square root of n times square root of kappa n. Okay, and you get this version. But this is not this theorem is not new. It is really equivalent to Phillips and Magdalenos IVX. What about in the mildly explosive, purely explosive case? So if the true x is say purely explosive or mildly explosive, then our IV estimator based on this combined instrument is again, this looks very messy. It has a limit distribution which is mixed Gaussian, okay, where x is always Gaussian. Y is always Gaussian, and x could be Gaussian if the true process was mildly explosive, so we get Cauchy in that case, or x is some unknown, random variable with unknown distribution, crucially not zero almost surely, and also independent from the normal numerator. So we get mixed Gaussian in both cases, and that's new because as far as we know, like the purely explosive case, that's the first procedure that can get you mixed Gaussianity, and standard, in this would imply standard normal T statistic. What about the rates of convergence? Well, in the purely explosive, in the mildly explosive case, the rate of convergence is this is the OLS rate, rho to the power of n times kn, multiplied by square root of the minimum over the maximum. Minimum over the maximum smaller than 1, so you always lose a little bit of rate. How much rate you lose depends on how much you shave from the true persistence of the process. That's in the mildly explosive case. In the purely explosive case, kn is a constant. So what you get is square root of rho to the power of n divided by square root of kappa 2. So you preserve the exponential rate of convergence of the OLS estimator, which is really fast, and the most you can lose is square root of kappa 2n, which is dominated by n. So again, the cost to pay for the fact that we can get mixed Gaussianities, we think is very small because we preserve the exponential rate of convergence, okay? What about the local unit root case? In the local unit root case, we have our estimator, our IV estimator has basically mixed Gaussian limit with this random normalization that depends both on kappa 1 and kappa 2, and has mixed Gaussian distribution with asymptotic variance that depends on this blue piece, which is the piece from Phillips and Magdalenos IVX, and this new red piece, that's the new piece that comes from the mildly explosive instrument. Okay, and so, you know, in general, like let's say that the true process was a pure unit root, and you base your, you will be choosing the near stationary instrument 66% of the time because the OLS is right, and the mildly explosive instrument 33% of the time. So this will be your frequencies, let's say, of choosing these things. Okay, predictive regression, we get the same results. I'm not going to show you the same equations. This is a lot of algebra, but everything is exactly the same as in the autoregression, and also everything is exactly the same in the local projection model with some normalizing constants, right? But the same results. The only difference, and this is an important difference, in predictive regression, we can allow the innovations in the autoregression to be serially correlated stationary linear process. So, which is really, really nice. So we have more general condition on the innovations, on the U innovations. And again, as I said, in the new version of the paper, we have heteroscedasticity like a la Garch. Okay, non-stationary oscillations, I mean, okay, this is why I avoided using, you know, having the full parameter space, because also I get very confused with left and right and absolute values. But let me just say that we can transform the regular process into an oscillating process into a regular process using this transformation -1 to the t, where, you know, the new transformed process is now, it has an absolute value, the same root with an absolute value. So using this transformation, we can do everything on the other side. With the only difference now is that now we're going to have 4 roots. We're going to have the near stationary root from before, phi 1, the mildly explosive root, phi 2, which both converge to 1 from below and above. But now we're going to have 2 oscillating roots, phi 1 minus, converging from the stationary part to -1, and phi 2 minus converging to -1 from the explosive side. Okay, and if you want to know intuition, again, remember you're building an instrumental variable that's going to have to be relevant, that needs to co-move with the process. And so, you know, the process is oscillating, the instrument oscillating as well. But it's oscillating in a way that it cools down the persistence to a level of either near stationary mildly explosive where we have central limit theorem. That's the game. How do we do the events? You know, we intersect. Our original event now has absolute value of rho hat -1. And we intercept this with rho hat OLS being positive or negative. So, you know, and all this, of course, is in the paper. We need to make sure these indicator functions converge arbitrarily fast, and, you know, that's there. So let me, because I understand what the time is, give you the main result of this is the main result of the paper. Like, so, you know, this is the most important part. And consider the IV based t-statistic based on the IV estimator, based on this combined instrument. This is your standard t-statistic Z prime X and Z prime Z inverse, you know, rho hat minus rho, the textbook thing with the IV. And also consider a confidence interval using this IV estimator where you use critical values from a standard normal. That's my phi, capital Phi is my standard normal critical values. And also consider the critical region for this test. This is the you know, the region where you reject the t-statistic, where you know, t-statistic exceed the critical value for given alpha level. So you pick some confidence level. So under assumption 1, right? So here we're working under assumption 1, and I will the t-statistic from equation 3 converges in probability to converges in distribution to standard normal. The critical region is asymptotically similar with correct asymptotic size. So basically, if you do lim over the infimum of arbitrary closed subintervals, so -infinity plus infinity, is also the lim sub. which of the probability of the critical region is alpha, the chosen size, and moreover our confidence intervals are have uniformly correct coverage 1 minus alpha for the chosen alpha. This is the main result. We have the exact same result for beta. I'm not even going to repeat it. With the only difference is now we have weaker assumption on the innovations. Everything else is the same. We just have the IV estimator for beta. So I'm skipping this slide. I have like 4 minutes, so let me, in the interest of time. So how do we go from assumption 1 star to assumption 1? We use subsequential arguments. So basically, for every subsequence, we consider for every subsequence of rho n, we can show that for a subsequence that belongs to one of the 3 classes that satisfies assumption 1 star. But in all these 3 cases, we have standard normal t statistic because mixed Gaussianity self-normalizes. Therefore, the original sequence must converge. And this is, again, the uniformity. We follow very, very closely arguments by Andrews, Chen, and Guggenberger. But I need to say that in addition, so this assumption 1, the fact that we can do this for an arbitrary sequence rho n converging to arbitrary point in the parameter space gives us uniformity overall. One of the things that the referees ask us is, well, in the explosive case, your OLS depends on the distribution of the innovations. So you need to show uniformity over the distribution functions of the innovation sequence. And that was not easy because then, of course, that's an infinite dimensional object and we had to work to show that. So in the new version, there's also uniformity over the sequence of distribution functions. So in terms of instrument selection, I'll say 1 or 2 words. So the negative roots are set to be minus the positive roots for simplicity. We slightly parameterize these things to be basically phi 1 is 1 minus 1 over n to the beta 1 and 1 plus 1 over n to the beta 2. So in the end, you have to pick beta 1 and beta 2 numbers in 0, 1. And then, we do something in the paper. So just to say, there is no optimal, there cannot be any optimal instrument because it depends on the true data generating process. And we want a procedure that works without knowledge of what the true stochastic nature of X is. And therefore, what we do in the paper is we know our worst case scenario in terms of size, in terms of finite sample size distortions. It's the pure unit root case in the predictive regression with very, very, very strong contemporaneous correlation between epsilon and u. That's like 99. That would be that's actually also the case that distorts the OLS the worst. So we pick that case and we say let's pick the B1 and B2 in 0, 1 such that we have a reasonable we do not exceed 6% size in that case. And the numbers that come out of this exercise is 0.85 and 0.7. So that's what I use for all of the simulations that you will see and that are in the paper and also for all the empirical applications. So there's a very large number of simulations in the paper. So we've tried to compare the predictive regression procedure because our procedure works in the 3 models without changing anything. So in the predictive regression, we compare size and power against Elliott, Moore, and Watson econometrica paper procedure. Against in the autoregression, we compare coverage rate and length of confidence intervals against the Andrews and Guggenberger procedure. That's for raw. And for the local projection model, we compare against Olea, Blockborg, Muller econometrica paper, which is the lag augmentation stuff that they have. So there's a large number of simulations. I plot them because if I show you tables, you won't be able to see any patterns. But let me just say, we're always blue and the competitor is always red. And I'm showing you different sample sizes like 200, 500, 1000. And in the horizontal line, you have 31 data generating processes. So here, like the autoregression is anything from stationary to local to unit root to purely explosive to oscillating explosive and all the intermediate stuff. So these are different data generating processes. This is the size and the 0 correlation in the things. So you can see we have a pretty good size. Now, if we go to correlation between the epsilon and the u, contemporaneous correlation very strong, like I think 0.9 0.9 here, or 0.99, I'm not sure. We get small distortions, but those disappear as the sample size increases. So we have like a very good, I mean, here, Elliott, Moore, and Watson procedure does not work outside 0, 1. It doesn't even work for 0, or like stationary oscillations. I am not sure why, but it should work here, but it never rejects. It never rejects under the null, it never rejects under the alternative. This is a negative correlation case. Again, I don't have time to tell you the blue and the yellow. I'll just say, you know, we have good size. They have some, I don't know, Elliott, Moore, and Watson, they do something here. And anyway, in terms of power, like if I had to take one takeout, is that we are a lot more powerful than Elliott, Moore, and Watson everywhere apart from the unit root. In the unit root case, in the exact unit root case, they're slightly more powerful. The differences are tiny, and crucially, we're valid on the right side of unity, and also at 0 and on the left side, which this procedure is not. They never reject the null. And the same for positive correlation, the same for negative correlation, exactly the same for the autoregression. If we compare it to Anderson-Guckenberger, basically, we have really good coverage in all DGPs, and we have shorter confidence intervals everywhere apart from the pure unit root case. But, you know, the differences are small and they disappear as the sample size increases. I'm not even going to talk about the, I'm not even going to talk about the local projection because the procedure of log workmore, I mean, it's not stable. It gives us, it was very hard to make that procedure work actually, and it has very poor properties because when you do lag augmentation, what they do in the unit root case, they have a root n consistency, whereas our consistency rate is much faster. It's close to n. So, you know, there is no point comparing. I'm going to skip all of this. So I think I'm out of time. Oops, I am out of time. The only thing I will say is the application that we added for the revision of the paper was basically to look for bubbles using the type of algorithms that Phillips and Yu and Wu have. So we applied the rolling, test where under the null we have unit root, and then the alternative we have rho greater than 1, and so we're looking for bubble episodes in the stock prices of this Magnificent 7, and so the shaded areas are the stuff we find. And so, sorry, I'm 2 minutes above time, but let me just briefly conclude to say we have this new procedure. It works for a regressor with arbitrary persistence degree. We have no discontinuities, standard normal t-statistics of 1.96. It's very, very simple to use because it's closed form, linear estimator, analytic expressions with critical values from the standard normal. So this is in contrast to existing procedures. It's actually pretty difficult for practitioners to use. And as far as we know, in the pure explosive case, it's the first distribution-free procedure. And, it is very simple to use. And, we are working on various extensions, including multivariate extensions, adding more dynamics, also having, more complicated dynamics, and having time-varying persistence. But the idea in all these extensions is always the same. You have a problematic regressor or vector regressor, and then you project it onto a space of a more well-behaved process that you control, and then you use the projection instead of the original process. I'm sorry for the 4 minutes over time.